This is our last lesson on counting and permutations combinations before we get into probability, which is coming very soon. So here I have a problem. We have 15 blocks numbered from 1 to 15, but these blocks are multicolored. We have the first 6 of them are colored red. We have the next 7 that are colored blue, and then the final 2 are colored green. If all these blocks were the same, we would have 15 factorial ways to arrange them. But because we have different colors, and for the purposes of this problem, we want to keep things nice and organized, we're going to attempt to keep like colors together. So all the reds have to be together, all the blues have to be together, and the 2 greens have to be together. The question is, how many ways can we arrange these blocks under those conditions? To start out, let's arrange the red blocks. We have 6 factorial ways to put the first 6 blocks in some kind of order. 6 choices for the first spot, 5 choices for the second spot, then 4 and 3, and so on. And we have 7 blue blocks, so we have 7 factorial ways to arrange them. And then finally, we have 2 factorial, just 2 ways to arrange green blocks. That is not the entire solution. This is assuming a specific order: red, blue, green. Who says red has to be first? What we have essentially is this. Here are our red blocks. Here are the blue blocks, and here are the green blocks. There's nothing that says red has to be first. We could have red be second, blue be first, green be last. Or we could have red first, green, blue. Or we could have blue first, green, red. Or we could have green first, red, blue, green first, blue, red. Those are 6 different ways we can arrange the groups of blocks. So what essentially we have here are 3 groups of blocks. Keeping the groups together, one group has to be first, one group has to be second, and then one group has to be third. Well, that's 3 factorial. And that makes sense. We have 3 groups, so 3 choices for the first group that goes first, 2 choices for the group that goes second, and then the last group, there's 1 choice. So not only do we need to shuffle within each color, so shuffle the 6 red blocks within that group, shuffle the 7 blues within that group, shuffle the 2 greens. We need to shuffle the groups as well. So this ends up being a rather large number. 6 factorial times 7 factorial times 2 times 6. And we get several million, about 43 million ways 43.5 million ways to shuffle all these blocks around. So in a problem like this, where we're keeping like groups together, things together, shuffle within each group, rearrange within each group, and then rearrange the groups themselves. Another example of this is, let's say you have various types of CDs. For those of you that still listen to CDs, you have a bunch of CDs at home and you want to keep them in some kind of order. So you put all your classic country in one group, you put all your classic rock in one group, and so on. So you have different ways to shuffle within each group, but then you can also shuffle the groups around. So maybe you put all the classic rock first, maybe you put the classic country second, and so on, or vice versa. Different types of books. If you have mystery, action, adventure, science fiction, and so on, you can rearrange those by groups as well. Oftentimes, car dealerships will arrange cars by group. They'll put some of the sportier, fancier ones inside the showroom, with a few of the larger pickups, SUVs, and then out on the lot, they tend to group things together. So we're going to put all our SUVs in this part of the lot. We'll put all of our smaller SUVs / larger four-door cars in this group, and so on. So that way, when you're looking for various things, they're easy to find. You don't have to run all over the lot to try to see every single type of one vehicle. If you're looking for a certain type of car, they're all in the same spot, all grouped together. And every once in a while, they will move those groups around for a couple of reasons. One, it kind of changes things up as they get new inventory in and they get old inventory out. And second most important reason is it allows them to at least start the engines up, move them a little bit, and so on. Otherwise, if the cars sit too long, bad things can happen to some of their mechanical parts. On to the next problem. Here we have a word, actually name of a city, with 7 letters. How many ways can we arrange these letters? And my hint is actually incorrect. My hint should be less than 7 factorial. This is less than 7 factorial. 7 factorial is the obvious answer because, we have 7 letters, 7 choices for the first, second, 6 for the second, 5 for the third, and so on. But there's a catch. If I switch those 2 letters, have I made a new order? Or if I just switch these 2 letters, if I just switch the 2 S's, have I made a new order? No, have not. In fact, all of these count as one order, not 8 separate orders. Because all I have done is switched the letters that repeat. So here, what I did here is I colored the letters that duplicate a different color. So now when I switch them, you can see that I switched them. But have I made a new arrangement of letters? And the answer to that question is no. It's still the same order of letters. Still the same order, still the same exact order, still the same exact order, all the way down the line. I have not made a new arrangement of letters. Now, if I were to switch the H and K, well, that would be a new arrangement. If I were to switch the O and the S, that would be a new arrangement. But switching two letters that are alike, and here I switched the two O's. That's all I did. Here I just switched the two S's. From here to here, I switched the two S's. That's all I did. I did not make a new arrangement. It's still the original one. So that doesn't count. We need a way to divide out all of these repeats. So we look at how many repeats we have. There are 8. 8 of the same thing. So we need to divide all those out. And here's how we do that. I have 7 letters. But I have 2 O's. If I divide by 2, I eliminate the repeats of just switching the O's. Divide out the repeated H's. I have 2 S's as well. 2 factorial times 2 factorial times 2 factorial. I take whatever item is repeated and divide by that factorial because I have 2 spots, 2 ways of just switching the same letters around. That doesn't change anything. 2 ways of switching the S's around without changing anything. 2 ways of writing the H's without changing anything. That's going to give me my 8. So we end up with 7 factorial divided by 8. And we end up with 630 ways. That's how many unique ways there are to arrange the letters in the word Oshkosh. Not 5,040. We are eliminating every single way of just switching things around. If I switch the S and the O, I have a new way to arrange the letters. Let me write that up. Switch the S and the O. The first S and the first O, I should clarify. But now, from this version, if all I do now is switch these 2 letters, or if I switch these 2 letters, or if I switch these 2 letters, I have not made a new arrangement. If I just switch letters that have the same underline, I have not made a new arrangement. So that's 8 ways of writing this arrangement, which we have to divide out. So this divides out all those possibilities. Here's another example, a little more complicated. You look at the letters in the word in the state name Mississippi, and you think, wow, 2, 4, 6, 8, 10, 11 factorial. 11 factorial is huge. Yeah, but we have a lot of repeats. We have 4 I's. Only 1 M. We have 4 S's to divide out. We have 4 factorial ways just to rearrange the S's without putting them in a new spot every time. 2 P's. So we're dividing out several things here. We're dividing by 4 factorial twice. And then we're dividing by 2. And we go from several million possibilities down to less than 35,000. The more repeated items you have, the fewer unique ways there are to arrange things. Term for this is distinguishable permutations. In other words, we want to be able to distinguish, we want to be able to tell if we changed something. If I write the letters OSH, out, and then have everybody leave the room, and then all I do is switch the O's, everybody comes back in, you're not going to be able to distinguish between the first one and the second one. You can't tell if a change happened. But if I were to switch, say, the first O and the second, or the first O and a K, you would be able to tell that I made a change. Or if I switched to the first O and the second S, that would be a change. That's distinguishable. You could tell that I made a change. The way we calculate distinguishable permutations is this. We take all the items factorial, and then we divide by the first item that repeats, however many times it repeats. And then if we have a second item that repeats, we divide by that item factorial. And we keep doing that until we run out of repeats. Things that don't repeat are just 1 factorial. Dividing by 1 doesn't do anything. So in our Oshkosh example, we had 2 O's, 2 AS's, 2 H's, 2 factorial 3 times. In our Mississippi example, we had 4 I's, 4 S's, 2 P's. Whatever item repeats, the number of times it repeats, factorial. Item that repeats, that number of times, factorial, and so on. Distinguishable permutation. Last thing for this first half of the unit. 4 people are sitting around a circular table. Keyword circular table. Circle. How many ways can we arrange them? Again, if you're thinking it's just 4 factorial, you are wrong. It's not 4 factorial. Here's why. Here I have 4 people that I just called A, B, C, D. And I put them around a table, gave them all a seat. And then I said, okay, now everybody move 1 seat to your left. Is this a new seating chart? No. Because look who everybody is sitting next to. In the red, A sits next to D and B. D is to the right of A, B is to the left of A. When A moves to this spot, D is still on their right, B is still on their left. When they move again to this spot, B is still to the left, D is still to the right. When A moves here, B is still left, A is still right. Those are the same 4 seating charts. All of those count as 1 seating chart, not 4. So again, we have this problem of counting things more than once. We have to divide all these out. So we have 4 seats, 4 ways to write the same seating chart. 4 factorial, we divide by 4 because that's the number of repeats we have. Let's say we have 5 seats. In this example, if all we do is slide everybody over 1 seat every time, we're going to have 5 different ways of making the same seating chart. 5 factorial divided by 5. If we have 6 seats, and then all we do is tell everyone, move 1 seat to the left, then move 1 seat to the left, then move 1 seat to the left, and so on. We will have 6 repeats. And hopefully by now you see a pattern. 4 factorial divided by 4 is really 3 factorial. This is really 4 factorial. This is really 5 factorial. Our answer is 1 factorial less than what we started with. 1 less than what we started with. 1 less than what we started with. Because we're dividing out that first number in the factorial chain. How about n seats? N seats. For a circular permutation, this is when we arrange things in a circle, n seats would be n factorial divided by n. What's n factorial? Well, that's n times n minus 1 times n minus 2, and so on, which you may recall is n times n minus 1 factorial. Because if I start the factorial here, n minus 1 factorial is just n minus 1 times n minus 2 and blah, 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 blah. I just took the n out of the chain. The reason I did that is so I could divide it out here. When we arrange things in a circle, it is n minus 1 factorial. I have 11 items, actually 12 items, the 12 Knights of the Round Table. There are 11 factorial ways they could arrange themselves on a round table. That concludes the first half of this unit. Next week, we will get into probability, so we will be using some of these techniques to help us calculate probabilities.